Okay, today we're going to do logical equivalence. And so I'm going to write down the definition of what it means for two statement forms to be logically equivalent and what it means for two statements to be logically equivalent. Remember, you need to know the difference between a statement and a statement form. If you don't remember, look that up in the previous lectures. Okay, so two statement forms are called logically equivalent if and only if they have identical truth values for each possible substitution of statements for their statement of variables. Okay, so that's kind of a lot to take in. Okay, but I think that we can make sense of this by me showing you how you check it. Okay, so here's what I'm going to do. I'm going to write down two statement forms. Here, let me do this. We will show that, so here's one statement form, the negation of P and Q. Okay, and the other statement form I want to write down is the negation of P and the negation of Q. And I will show that those are not logically equivalent. Here's the symbol for logically equivalent, is a 3-bar equal sign. And I want to show you that these two are not logically equivalent. And there's the symbol for that. Okay, so remember now, these are statement forms, not statements. They're just made up of variables and symbols. So they're neither true nor false on their own. But this statement form right here, for instance, whether that's true or false depends entirely upon whether or not P stands for something true or false and Q stands for something true or false. Okay, and how do you figure out all those combinations? You do a truth table. So to see if two statement forms are logically equivalent or not, you do a truth table for both of them and see if the truth tables match up. Okay, so here's what I'm going to do. We're going to make a fairly large truth table here. That should be wide enough. Okay, and I'm going to make a truth table for that statement form first. Okay, and I'm going to build it up in pieces. So what are the variables involved? Variables are P and Q. So I need to start with a column for P and a column for Q. Okay, those are my variables. And I'm going to write down the 4 possible combinations of truth or falsity for those two. We could have them both true, P true and Q false, P false and Q true, or both false. Okay, now let's do that part right there. So here's what I'm going to do. I'm going to make a column for P and Q. I'm going to build up the statement form, the negation of P and Q. So I start with P and Q, and then from those I'm going to write P and Q. And then once I complete that column, then it will be easy for me to do the negation of that. Okay, so P and Q is a conjunction. I showed you yesterday how to fill in a truth table for a conjunction. It is only true when both components are true. So when P is true and Q is true, P and Q will be true. Otherwise, in all the other 3 combinations, P and Q will be false. It's only true if both parts are true. Okay, now the next one is the negation of that. How does that work? When a statement form is true, its negation is false. When a statement form is false, its negation is true. I'm looking at this column to figure out how to fill in this column, because this one is just the negation of this one. Okay, so that takes care of this. Now, in the same truth table, let's build up a section for here, for that statement form. That's the conjunction of the negation of P and the negation of Q. So let's make a column for the negation of P, and let's make a column for the negation of Q, and then we'll do a column for the conjunction of those two things. Okay? So to fill in here, I need to look at here. This is the negation of this. So when P is true, the negation of P will be false. When P is false, the negation of P will be true. All right, now to fill in this column for the negation of Q, I need to look at the column for Q and do the negation. When Q is true, its negation is false. When Q is false, the negation is true. When Q is true, the negation is false, and when Q is false, the negation is true. Okay? And now here, I want to do the conjunction of these two. Remember, a conjunction is true only when both pieces are true, and it's false otherwise. So in the first row, both pieces are false, so the conjunction will be false. In the second row, the negation of P is false, so this conjunction will be false. In the third row, the negation of Q is false, so the conjunction will be false. In the last row, both parts are true, so the conjunction will be true. Okay? Now, to show that this statement form is not logically equivalent to this statement form, what we do is we compare these two columns and we see that those two columns don't match. Okay? So that means that these two statement forms don't have identical truth values for each possible substitution of statements for the statement variables. Because these four rows show all possible truth and falsity of statements substituted into the variables. And what we see in these two columns is that our two statement forms we're asked about don't have identical truth values for each of those possibilities. In particular, for this possibility, those two statement forms don't have identical truth values, and also for this possibility, they don't have identical truth values. So they don't have identical truth values in all possibilities. So we say they are not logically equivalent. Okay? So that's for statement forms. Now let's write down what it means for two statements to be logically equivalent. Two statements are logically equivalent if and only if they have logically equivalent forms. When identical statement variables are used. Okay? So basically what that means is this. If you want to know if two statements, which are actual sentences, not just symbols, if you want to know if two statements are logically equivalent, what you do is you write down the statement form for each statement using the same variables, and then you do a truth table to see if those statement forms are logically equivalent. Okay? So that's how logical equivalence works. Now, we can get a lot of laws of logic in this way. Okay? So I'm going to prove for you several laws of logic. Okay, so the first one is called, there's two of them, called De Morgan's laws. Okay, and what that says is that the negation of a conjunction is logically equivalent to the disjunction of the negations of the variables in the conjunction. So in other words, not P and Q is the same thing as not P or not Q. Okay? And how do we prove that? We're going to do a truth table. Okay, so let's put P and Q here. And let's do all the possible combinations of true and false. True, 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 false, false, true, false, false. Okay. Let's now make a column for the conjunction of those two, P and Q. Conjunctions are true if and only if both components are true. So this should be true, and then false in the other three possibilities. And then I would like to make a column for the negation of that. Because that will finally give me this side here. Okay, so we're negating this. So we're going to get false, true, true, true. Okay, so there's a column for that statement form. Now, let's build a column for that statement form. So let's do a column for the negation of P, and then a column for the negation of Q, and then we'll do a column for the disjunction of those two. Okay, so to fill in the negation of P, I look at P and I negate it. So that'll be false, false, true, true. To fill in the negation of Q, I look at Q and I negate it. So that will be false, true, false, true. And now for the disjunction of those two, I look at these two. And remember from the previous lecture, a disjunction is true if and only if one or both components are true. So it'll be false in this case when both components are false, but in every other case it's true. And now I just compare this column and this column, and you see that they're identical, and so that means that those two statement forms are logically equivalent. Okay, so that's one of De Morgan's laws. There's another one. that says the negation of a disjunction is equivalent to the conjunction of the negations. And what I'm going to do is leave for you to make a truth table that shows that those are logically equivalent. Okay? All right. Here's some more laws. There's two laws called the commutative laws. There's one for conjunctions and one for disjunctions. Okay? So the first one says that the conjunction of P and Q is logically equivalent to the conjunction of Q and P. Okay? Let's prove that. This won't take a very big table. Okay, so let's start by putting in our variables P and Q. And we'll do the 4 possible combinations of true and false. Both true, true, false, false, true, both false. Okay? Now let's do the conjunction of those two. A conjunction is true only if both components are true. So in this case, P is true and Q is true, so the conjunction of P and Q is going to be true. But in all other cases, one of the two is false, and so the conjunction will be false. Okay? Now let's do the conjunction of Q and P. So again, a conjunction is true if and only if both components are true. So in this case, Q is true, P is true, so the conjunction of Q and P is true. In the other 3 cases, one or both are false, so the conjunction will be false. And then I compare this column and this column, and I see they're identical, and so that means that those 2 statement forms are logically equivalent. Okay, now the commutative law for disjunctions I'm going to leave for you to prove, and it says the disjunction of Q and P, which we would read Q or P, is logically equivalent to, oh sorry, I said that in the wrong order. That's P or Q, okay, and that is logically equivalent to Q or P. All right, and you can show that with the truth table. And I'll leave that. I'm going to leave that for you to do the truth table for that second one. Okay. Okay, next pair of laws are called the associative laws. Okay, a little bit longer here. We're going to have 3 variables. Okay. So the associative law for conjunctions says that the conjunction of the conjunction of 2 things and a third thing is equivalent to the conjunction of the first thing and the conjunction of the other two. Okay? So let's prove that. This truth table's got 3 variables, so it's going to be a little bit wider. It's going to have more columns. It's also going to be twice as long, twice as tall, because since there's 3 variables, there's going to be 8 possible combinations of true and false. Okay, so let's put our variables P, Q, and R. And let's go ahead and just do that first. So let's write down all possible combinations of true and false for those 3. Okay, so there's a possibility of all 3 true, or P true, Q true, but R false, or there's P true, Q false, R true, P true, Q false, R false, P false, Q true, R true, P false, Q true, R false, P false, Q false, R true, and all 3 false. Those are the 8 possibilities. Okay? You gotta make sure you get all 8. I'm going to give you a quick little piece of advice. However many variables you have here, which in this case is 3 variables, that means that here you're going to have 8 possibilities, because it's going to be always 2 to the 3. It's always 2 to the power of how many variables there are. You write them in whatever order you want, okay, but you figure out the 2 to that power many. You figure out those different possibilities and write down all of them, okay? So if there's 4 variables involved, then there's going to be 2 to the power 4, which is 16 possibilities of true and false combinations, okay? All right. We won't usually see more than 3, though. Okay, so what do I need here? I need to, whoops. Hold on here. Okay, I need to build up this statement form there, so I'm going to do a column for P and Q, and then after that I will hook onto it and R. Okay, so to do this column right here, that's a conjunction of P and Q. When are conjunctions true? Only if both components are true. So where's the rows where P and Q are both true? Here's one, and here's one. In all of the other rows, one of them is false, and so their conjunction will be false. Okay? All right, now to do this one, which is one of the rows that I'm wanting, one of the columns. That's this guy right here. Okay, to do that, I have the conjunction of this and this. When are conjunctions true? Only when both components are true. When does that happen? Here, and that's it. So that'll be true in that possibility, but false in all of the others. Okay? So there's a truth table for that statement form. Now, let's just add on to the same truth table and add in that statement form. Okay? So I want to make a column for Q and R, and then I'll make a column for P and that previous one. So Q and R, that's the conjunction of this one and this one. When are they both true? I see 2 times, here and here. In every other possibility, one of the two, at least one of the two, is false. Okay, and then the last one is the conjunction of this one and this one. When are they both true? The only time they're both true is right here at the top. So this column should be true and then the rest false. Okay. And now I'll just draw your attention to the fact that that column is identical to that one, which means that this statement form is equivalent to this one. Okay? And the other associative law, which I'm going to leave for you to prove, is same thing except with disjunctions. It says the disjunction of P and Q with R is equivalent to the disjunction of P with the disjunction of Q and R. Okay, we're going to do one more pair of laws, which are called the distributive laws. There will be 2, and like the other ones, I'll prove the first one for you. You can prove the second one on your own if you want. Okay, so the distributive laws, these have to do with combining a conjunction and a disjunction. Okay, so the first distributive law says that if you have P and Q or R, that's logically equivalent to P and Q or P and R. Okay, I'll go ahead and write down the second one. The second one says P or Q and R is logically equivalent to P or Q and P or R. Okay, let's prove the first one with the truth table. So we have 3 variables again. P, Q, and R. So there's going to be 8 possible combinations of true and false. You saw me list them out individually in the previous example. Okay, so this one I'm just going to go ahead and write them out. Okay. I have a strategy I use so that I can write them out quickly. You can develop your own strategy. The only thing I'm going to say about it is I told you how to find how many there are. It's 2 to the power 3, so there's going to be 8. And then you need to find the 8 different possible combinations of T's and F's. However works best for you. Okay? All right, so let's work on this thing here. I already have a column for P. Let's do a column for Q or R. And then we'll do a column for P and Q or R. Okay, so right here, the disjunction of Q with R. So I need to look at Q and I need to look at R. Disjunctions are true as long as one of the two are true. So that'll be true in that case, and that case, and that case. True here, true here, true here. Another way of saying is that a disjunction is only false if both components are false. Okay, and now we'll do P and this. That's a conjunction of two things. It's only true if both components are true. So when does that happen? That happens here. And it happens again here. And where else? Anywhere else? Here. Let's see, anywhere else where they're both true? No, in all the other rows, at least one of those two is false. So there we have the truth table for this. Okay, now let's make a truth table for this statement form. So I'm going to need a column for P and Q, and a column for P and R, and then I can put those together in a disjunction. Okay. So here I have the conjunction of P and Q, which is true if both P and Q are both true, and false otherwise. Okay, and here I have the conjunction of P and R, which is true if both P is true and R is true, which happens in those two rows, and it's false otherwise. Okay, and then finally we're going to do the disjunction of these two. Disjunctions are true as long as one of the two components are true. So it's going to be true here, true here, true here, and false the rest of the time. Okay, let's compare this column with this column. You see that they're identical? So that means that this statement form is equivalent to this statement form. Okay? So that's how you prove that statement forms are identical, equivalent, or not. And you just learned 8 important laws of logic: 2 distributive laws, 2 associative laws, 2 commutative laws, 2 De Morgan's laws. Okay? Now, one other topic for today: tautologies and contradictions. Okay. So let me write down this definition here. A tautology is a statement form that is always true we could just put a period right there and that would be a fine definition, but I'll give a little bit more information in case somebody says, what do you mean by always true? So what that means is it's always true regardless of the truth value of the truth values of the individual, let's say, components. That's what a tautology is. Okay, so I'm going to show you some famous tautologies. Okay, one is called the law of excluded middle. The book has another name for it, though. The book calls it negation law. Okay, and it is this statement form: P or not P. Okay, so what do I mean when I say that's a tautology? Let me show you what I mean. We're going to do a truth table. This just requires a small little truth table. Very small. Because there's only one variable. So, let's put P here. That can only be true or false. Okay, let's make a column for the negation of P. Well, then that would be false, true. And now we'll make a column for the conjunction of those two things. Disjunction. Okay? A disjunction is true whenever one of the two components is true. In both possibilities, one of the two components is true. So that statement form is always true. And that's called a tautology. In the book, it does this weird symbol. It says that is equivalent to, and then it gives this really fancy looking T. I actually don't like that. I think that gets very confusing for students. So I do not write that. Okay? Those symbols the book uses to say that it is a tautology. Okay, but I just say that. I say it's a tautology. I don't write those symbols. Okay, and tautology just means always true. Okay, now that's what a tautology is a statement form that's always true. Okay, a tautological statement is a statement whose form is a tautology. So I'll give you an example. I am hungry. Or I am not hungry. That's a tautological statement because its form is this. Suppose I represent that statement, I am hungry. That's a statement. I am hungry. It's either true or false, so it's a statement. Okay? Let me represent that by P. Then I am not hungry would be the negation of P. And the form of this statement is P or not P. That's the statement form of that statement. And that statement form is a tautology because we just proved that up above. It's the law of excluded middle. So since the form of that statement is a tautology, then that statement is called a tautological statement. Okay? Now, I want to, by the way, just point something out to you. Notice that for the negation of I am hungry, I wrote I am not hungry. I didn't write I am full. You see what I'm saying? I specifically said not whatever it said in the first statement. You should be in the habit of doing that when you're doing logic. Okay? Because not everything, the words are not always black and white, you know. Does full and not hungry mean the same thing? Not necessarily. Okay, but to see that, a better example is to use hot and cold. If I said I am cold or I am not cold, I would definitely not say I am cold or I am hot, because not being cold isn't the same thing as being hot. So if you mean not cold, you should say not cold. Otherwise, you're going to get into logical problems. Okay? When you're just speaking in your life, you know, then it's not a problem. I'm talking about when you're doing logic. Okay? If you mean not something, then it's best to say not that and not find, you know, you don't want to use some third word that you think means the same thing. That's a dangerous thing when you're doing logic. Okay? All right, last thing for today is contradictions and contradictory statements. Let me look here. Okay. So I'm going to label this contradictions. Okay. A contradiction is a statement form that is always false. Regardless of the truth values of each component. Okay. So an example of a contradiction could be P and not P. That's a contradiction because if I make a truth table for that, you'll see that it's always false. Whether P is true or false, let's look at P and not P. So when P is true, the negation of P is false. When P is false, the negation of P is true. So the conjunction of those two things is never true because they are never both true. So you see here that this is always false. So that statement form is called a contradiction. Okay, and then a statement whose form is a contradiction is called a contradictory statement. A contradictory statement is a statement whose form is a contradiction. So an example of that would be I am tall and I am not tall. Notice I said not tall, I didn't say short. Okay. If I use P to represent I am tall, then this would be the negation of P, and that sentence is the form of a conjunction of P and its negation, and that statement form is always false, so it's a contradiction. So that statement is a contradictory statement. Okay, that's it for today.